Getting new tools in the shop is exciting. Blowing up those new tools because you don't have the right voltage available is also exciting, but not in a good way. So today we're going to talk about buck and boost transformers. Welcome back to Cloud 42, I'm James. Well, if you saw my last video on wiring a plasma cutter for CNC, then you know that I'm getting geared up here in the shop to be able to do sheet metal work. And this is the next step in that process. This is an electromagnetic sheet metal bending brake. This one's made by Bailey. And the way this works is it has a large electromagnet in the top surface here and a steel clamping bar that goes over that electromagnet. So you can just slide a piece of sheet metal underneath this, engage the magnet to clamp it down, and then raise the leaf to make your bends. Now, this bar has a bunch of slots in it so that to make clearance for the edges of shallow pans. It also comes with a solid bar, comes with a narrow bar, and it comes with some little pieces of clamping bar that you can pin together in various lengths for doing deep boxes that you wouldn't necessarily even be able to reach on a traditional finger brake. Now, as flexible as this is, the reason that I went for the electromagnetic brake is because of the size. This thing is really, really shallow. There is a little tooling tray that'll go on here, but even with that, this thing is only a foot deep and will fit with the legs into a little 2-foot wide slot. I can slot it in against a wall, maybe in front of the furnace here. I can put it, anywhere in my shop, and it doesn't take up much space. And it's only about 400 or 500 pounds. It's relatively easy to move around. And so for a small shop, this seemed like a much better fit than a less expensive, but much larger and heavier and bulkier finger brake. Now, the one thing about this that was really interesting is that the manual and the website are both super clear about the voltage requirement. It's 220 volts AC plus or minus 5%, so maximum of 231 volts. Power in my shop here is 240 volts nominal. Most days it's about 244, and that's too high. It's outside of the spec. And in fact, when I opened it up and looked at it, they actually have a custom sticker on the power cable that says 220 volts plus or minus 5% only, and another one that says input power 220 volts 60 hertz. So they've gone to a lot of trouble to make sure that you know that it's 220 volts only. And in fact, there are notes in the manual and on the website about the warranty being void if you run it on higher voltages. Now, the internet is full of people, and those people have opinions, and a lot's been written about this. So if you've used your electromagnetic sheet metal brake at 275 volts underwater on the moon since 1969, go ahead and leave us all a comment down below and let us know that it's not a problem at all. But for me and my money, and a machine like this is a little over $3,000, I think $100 for a buck boost transformer to lower that voltage into the specified range is just good insurance. Now, I've already picked up a transformer. In fact, I've already got it bolted here on the back, but let's roll back the clock a couple minutes, go over to the bench and take a closer look at what a buck boost transformer is and how it works. I've got the transformer over here on the bench, and if we open it up, it comes with some literature, which we'll ignore for a moment. And it's got a whole bunch of wires. Now, here are the input wires. I added these, but these are the wires that come with the transformer. There are a whole bunch of these, and you might expect that you would just have 2 wires for the input and 2 wires for the output, but these transformers are a little bit more complex. Let's talk for a minute about what's going on here and how this works. Now, if we take the simplest case of a transformer, which would be a step-up or step-down transformer, commonly you would see step-down transformers in low-voltage electronics. And a transformer, in its simplest form, is just a couple of coils of wire. So you have what's commonly called the primary coil, some kind of magnetic coupling, and a secondary coil with a smaller number of turns. So I'll just make up some numbers. Maybe we have 100 turns on the input here and 10 turns on the output. And what that means is if we put in, say, 120 volt mains voltage, which is common in the US, That AC current will create an alternating magnetic field, which will then induce a current in the secondary. And because of the turns ratio, we get a lower voltage. 100 turns on the input, 10 on the output, then 120 in, you get 12 volts out. And then you'd run this through some diodes to rectify it and capacitors to filter it, and you get a DC voltage, low DC voltage at 12 volts that you can use for your application. And I will just ignore the fact that you actually get more than 12 when you rectify for DC, but we'll ignore that for the moment. But the other thing that happens here is that you get a current increase. You may have 1/10 of the voltage, but you then potentially have 10 times the current. So if we've got 1 amp AC, or let's do it the other way. If you're drawing 10 amps on this 12 volt coil, that's going to require 1 amp on the input. So because of the magnetic coupling, these devices are very efficient. There is some resistive loss in the wires, and there's potentially some loss depending on the core material from the magnetic field alternating, inducing currents flowing in the core material itself. But in general, these can be designed to be very efficient, so you can move a lot of current through a device like this without producing very much heat. Whereas if you just used a resistive divider to do this, like a dropper resistor, you'd be wasting 90% of the energy you put in as heat. And for a high power application like what we have here, that would be completely unworkable. The other thing that is good to know about transformers is that they are magnetically coupled, but they are not galvanically coupled, which means there's no, they're electrically isolated. This 12 volt AC voltage on the output can float anywhere at any voltage level relative to the input. I mean, subject to the withstanding voltage of the insulation in the transformer, but they're not connected electrically. So when you're using your low voltage electronics, if you touch them, you're not connected directly to the mains, at least in a traditional transformer power supply. Now, if we were going to use a transformer like this for our application, we would need a pretty large transformer because we're talking about a large primary and an almost equally large secondary, because we're talking about 240 volts and 220 volts. So this is like a transformer with two primaries if we're comparing it to the small signal or the small power transformer for that we typically would use for hobby electronics. This is going to be big because we need 10 amps on the output. So we're talking about potentially 2.2 kilowatts of power. And that's going to be a lot of copper and a lot of physical size and weight, a lot of material. This is not the most efficient way to do this. A much more efficient way is something called an auto transformer. Now, in an auto transformer, you have one coil with multiple taps. So we might have one big coil, but then have another tap attached at some point in there. So you would get the same kind of effect that you get with primary and secondary. You might put 240 volts input and get your 220 volts output, but this 220 volts is across part of the same coil that's used for the primary. And so you end up with only one coil. This is much more efficient. And in fact, this is exactly how a variac works. You actually have a brush that can move along this coil and tap it off at different points to change the voltage. This would be a much more efficient way to do what we need to do here, stepping down 240 to 220. Now, you don't have galvanic isolation. These are connected, and so you do have, there is a voltage between these legs, and so you don't have electrical isolation, but for this application, that doesn't really matter. Now, a more flexible way to do this, rather than having a single coil with a tap that you can't change, would be to build your transformer with a number of coils all around the same core. I'm going to draw the magnetic core. I didn't draw it here. And you can then connect these together, and they will behave as though they were a single coil. And in fact, you can take a transformer like this that has a primary and a secondary, and you can just connect one end of the secondary to one end of the primary and build a structure that looks just like this. And so you might have, in the case of this transformer, this would be intended to be, say, 120 volts here, 120 here, 12 here, 12 here. So if we wanted to get our same effect here, 240 to 220, we might connect the 240 across here and tap off our 220 here. And because you've got a bunch of different coils, you could run the different coils in parallel or in series in a bunch of different combinations to get a bunch of different input and output voltages. And that, in fact, is exactly what's going on here. This is labeled as the high voltage being 120 by 240, and that's what's going on. There's two 120s. You can connect them in parallel or you can connect them in series. And then low voltage, it says 1224, and that's because there are two 12-volt secondaries. And if we pull up in the literature that came with this thing, there's a great big chart here that you probably can't read that has low voltage and high voltage combinations, and then it tells you which model of transformer you want and which diagram to use to wire it. Now what we have here is the model A, which is the 120 by 240, 12 by 24. And we can look down this chart and say, well, on the high voltage side, there's 240, step down to 200. That's not what I want. 240 to 212. No, here, 240 to 218. That actually sounds really good. And I could step up from 218 to 240. But since I have 244 volts and I want to go to 220, this ratio is about the same. That's what I want. Model A, which is the transformer I have, diagram 4. And if we look down here at diagram 4, you can see this looks very much like what I drew right here. You have the 220 volt coils in series and the two 12 volt coils in series. Your high voltage is across the outside, your low voltage is across just the primary coils. And that is exactly what we need to wire up. All of these terminals are labeled, so we can just make the connections. And if we had a different need for a different combination of voltages, we could just read that off the table here, choose which model of transformer, and choose which wiring diagram to use. But of course, there's more to selecting a transformer than just the voltages. We also have to make sure that it can handle the current or the power or the VA that we need for our application. So let's talk briefly about that. There are calculators that you can use online to calculate what you need and select the kind of transformer. And in fact, that's what I did to select this one, or to select one similar to it, and then locate one from a supplier that I could get quickly. But let's talk a little bit about how transformers are sized. They are sized based on VA, which is volts times amps. Now, this is similar to power, which would be watts, but it's not exactly the same thing. If the voltage and the current in an AC waveform are exactly in sync with one another, meaning that when the voltage is at its highest point, the current is at its highest point, then VA will be equal to power in watts. When they're out of sync with one another, these values can be different. So you may have a relatively high VA, like 200 VA, but you may be only putting 100 watts, and that would be a power factor of 0.5. That's what the power factor means when you see that on an electronic device. It's a ratio of the power consumed to the VA. And the reason that this matters is because the wires need to be sized to handle the current in amps. So if you have a say 100 watts of power that you need, but because you have a low power factor, you actually need enough current to support 200 VA, well, now you need twice as much copper in your electrical distribution system and in your device to be able to support that. So let's talk about what that actually means here in terms of sizing a transformer, because this is a 0.5 kVA, or this is a 500 VA transformer. Well, that doesn't make any sense, because what I actually am trying to run here is a 220 volt device that requires 10 amps, and that should be 2200 VA. So why don't I need a 2200 VA transformer for this? Why am I able to get away with a 500 VA transformer? Well, the reason is because of the way the current actually flows in the coils. So if I draw these coils the way we're going to connect them, you have the low voltage here, and you have the high voltage here. So the high voltage is coming in, this is going to be 240 volts, and the low voltage is coming out, 220 volts. But let's talk about where the current is actually moving. So if the low voltage here is 220 and the high voltage is 240, then what that means is that extra 20 volts is across right here. Now, we're not doing anything with that, that's just a drop. So you have 240 in, 220 out. But where is the current actually flowing? So if we talk about the current, you have the current flowing from the high voltage side. That's not really going to show up very well. You have the current flowing down, going through our device and returning here, and then where does it go? It's actually flowing, the majority of the current is flowing across here and back up. There is very little current. The only current that's flowing through this portion of the circuit is just enough to create the magnetic field to induce the current here. So if the source were on this side pushing this way, we have some current going through that coil in order to induce the current in this part of the coil so that we can drive the current out to our load. Now, it actually works in reverse here. You have current flowing through here. That's creating a magnetic field that's inducing current here, which is adding to the output. So when we go from our 240 volts down to 220, the current is actually increasing. And the reason for that is because some of the current is coming out of this coil induced from here. You can ignore that, but the point being that the vast majority, this 10 amps that we need here at the load, that is flowing through these two coils. It's not flowing through these two coils. And so as a result, we need a transformer that can handle the current here. And if this is 20 volts, 10 amps, that's 200 VA, which means that our 500 VA transformer will be plenty to handle that current flow. Because again, we're not having to measure this because that's not where the current is flowing. And this is the reason why these buck and boost transformers are so efficient, because your entire coil does not have to handle all of that current. You only really have to handle it in what would traditionally be called the secondary. And in fact, if you look at the transformer, the high voltage wires here are small. I think these are 12 gauge, or they might even be smaller than that. Are they labeled? I think they're 16 gauge, and the secondary wires are 10 gauge. And if you used a traditional primary-secondary transformer, you'd have to have 10 gauge wire and larger coils on both sides of the transformer. So this ends up being a lot more material efficient. Now you could sit down and do all of this math and figure this out, but like I said, there are online calculators that figure this out for you. So you put in your voltage for your supply, the voltage and the current needed for your device, and it will calculate what size of transformer you need and which standard configuration of voltages you need. And I'll put a link to one of those calculators down in the description. But for now, I think we just need to get this thing wired up and put on the tool. To make all of the wire connections here in the transformer, I am going to use what are called lever nuts. And I've got a whole package here of different sizes. These are made by Wago, and the way they work is there is a lever that opens, you insert the wire, and then clamp it down on the wire. So I've got some little scraps of wire here I can show you. So I'll just strip the wires. This is Knipex wire stripper. These things are fantastic. I will put a link down in the description. But you can just set your size and strip the wire. Just open up the lever nut, insert wire, close lever nut. So in terms of cleanliness and convenience and security in making these kinds of wire-to-wire connections, these things are fantastic. And that's all you got to do. And in fact, these have a little tiny hole in the tip for your meter, and you can actually stick a meter probe in the end and measure voltages without opening them. And of course, these can be reopened and the wires extracted with very little effort and with very little drama and damage to the wires. So compared to wire nuts, twist-on wire nuts, these things are just fantastic. Now, because I've got a couple of different size wires in here, I ended up needing a couple of different size wire nuts. So these ones are good for 24 to 12 gauge, which is 0.2 to 4 square millimeters. And then I've got some larger ones that are good for up to 30 amps, and these are good up to 10 AWG wire, or in this case, which would be 0.5 to 6 square millimeter. And I've got these in both 2-contact and 3-contact versions. They also come in strips up to 5, and I don't know, maybe they make more than this, but so for wiring in electrical boxes, these things are fantastic. One thing about this is that this transformer has aluminum wire. And so in order to make aluminum wire connections to nuts like these that have copper, you have to use some kind of a corrosion inhibiting paste. This one is called Oxguard. Wago actually makes one of their own that comes in a syringe. I didn't have any of that available where I live. I would have to mail order it. So I picked this up, the Oxguard, and I just put some of it in a syringe, and I will just squirt a little bit down into the wire nut as is called for by their instructions before I insert the wire, at least for the aluminum connections, to make sure that the aluminum wires are fully protected from oxidation. Otherwise, the aluminum against the copper will oxidize over time and build up and start to overheat and melt things, and that's bad. So I've got my wiring diagram here, and I am just going to start connecting things together. Now I've got my all the wires from the transformer, and these are all labeled. And then I've got my input. I've actually just run my input cable. This is SJ00W, so Service Junior oil resistant cable, and this is 12-3, so these are 12 gauge conductors, ground, and the 2 legs of the AC, and then the output is it's actually a little bit smaller gauge, but this is just the cable that I cut off of the tool itself, and so that's my output on the low voltage side, and I will just make all of these connections. The cables on these are just super frayed, so I will clip them off and restrip them. Okay, that's all of the connections made. Those are pretty simple. And I just used the antioxidant grease. In fact, I used my whole syringe and just used that on the aluminum wires. The copper ones I just went ahead and put in. The last thing I've got are the 2 ground wires, and those need to be connected to this ground stud on the side. Then we should be done. And there we are. Let's just stuff the wires back in here, button it up, and go put it on the tool. So I've got the transformer now mounted on the back of the brake. I just drilled and tapped some holes and put it on here with some socket head cap screws. This is the original power cable. Just cut that down, routed it into the box, and this is the supply from the wall. So let's plug this thing in and give it a try. Now I've got this thing on wheels right now on a couple of moving dollies. That is not a good long-term plan, but that will work for now. So let's look at how this works. We can power it on, and then there are a couple of different settings here. Clamping for bending or continuous light clamping. The way this works is when you energize it, you can use a foot pedal, which I don't have plugged in, or you can just hit the switch here. It'll turn on a low power clamping force to pull down the bar. And then when you actually pull the leaf up, it energizes it to full strength. And you can hear that. And we put it back down, it goes back to just the light clamping. Then when you press the stop button and hold it, it runs a 12 volt signal, or 12 volts DC, back through the coil in the reverse direction to demagnetize it and get it to release. Now you can also put it in a continuous light clamping mode. And in that mode, when you pull the handle, it doesn't increase the force. So if you're just doing thin sheet metal, you don't need the full clamping force. You can leave it on the continuous light bending. So I'll just go ahead and leave it on the normal clamping for bending. I got a scrap of sheet metal here, and let's just slide this in and make a bend. Now I'm not making anything in particular, just got some scrap here. We're just gonna put some bends in it. So clamp and that is that. And this is fairly light gauge. This is aluminum, but you know, there's no reason. This will bend up to, I believe, 16 gauge steel and 20 gauge stainless steel is how it's rated, and that's for the full 48-inch width. I've read, some people have said that you can actually bend materials that are heavier than that, but you know, we'll see if the time comes that I need to do that. Pretty nice. We'll definitely be putting this tool to use. So we've got this wired up on here and we know that it works, but I actually want to come in here and do some measurements because we saw when I was drawing diagrams, I talked about how the current flows, and I want to actually do some measurements and confirm that and make sure that that's really what's happening. It also is really good for me to take something that is theoretical and make it practical. So it's not just math, it's also intuitive. I mean, I can follow the directions, I can use the calculator, I can contact the manufacturer and select the right transformer. But over and above that, I want an intuitive sense of how it's actually working so that in the future, when I face a similar situation where there are no instructions, I can design my own solution because I have an intuitive sense of how this stuff works. So let's take some measurements here just for fun and see if what I said is actually true. So the current in the secondary, in the output at lower voltage should be higher than the current drawn from the input. It also should, we should see a lot of current in the low voltage secondary coils and almost none in the high voltage primary coils. Let's see if that's really true. So let's measure the output to the tool first, and I'll just go ahead and reach under here and put it in the full clamping mode. And I'm seeing 17.5 amps. And that's on the 220 volt output. So if we switch back over to the 240 volt input, the current should actually be a little bit lower because as we lower the voltage, we should be getting a current increase. Yeah, 16 amps even. So that current is a little bit lower. So that 16 amps is being stepped down in voltage, but up in current. Now the primary should be carrying very, very little, just an amp or two. And let's see what it's carrying. And there it is, 1.5 amps. So sure enough, just like we predicted, the primary is actually carrying very, very little. And so that all checks out, and the fact that the primary is carrying so little current and the secondary, the low voltage secondary, is the only part that carries the actual high current for the load, that is the reason why these transformers can be so small. That's why we can use a 500 VA transformer on a 2200 VA rated tool. Now, honestly, the nameplate on this thing says 10 amps at 220. I'm measuring more like 17. What's going on there? I don't actually know. If you know, go ahead and throw that down in the comments. I'm just going to assume we're all cool. I'm going to follow the numbers on the nameplate. I did verify the output voltage is correct, so we're not overvolting it and drawing more current. And nothing seems to be getting warm. This all seems to be functioning normally. No sparks, no fire, no flames, no smoke. So I think we are going to be good. I'll go ahead and button this up, and this tool is ready to use. Well, that's all I've got for you today. If you enjoyed the video, give it a thumbs up. Feel free to subscribe to the channel, and you'll be seeing more of this tool in the very near future. Thank you for watching.